Right, well, it's time to start, so let's start. Here. Pass this around. Everybody gets signed in. Okay, yep, my audio's working. So we're looking at collisions and conservation of momentum as opposed to conservation of energy. So just a quick recap. We looked at the example of two rail cars. One's moving at 24 meters per second, and the other one is sitting stationary. When the two hit, the couplers interlock, and it becomes a perfectly inelastic collision. Now let's look at how the momentum is conserved, and then look at the implications to conservation of kinetic energy. The momentum before must equal the momentum after. Well, the momentum before, P2, is 0 because the velocity is 0, so it's 10,000 times 24 meters per second. And that must equal the 10,000 kilograms plus the second 10,000 kilograms times their common velocity, since they're now one unit. And we can find V final pretty easily if we divide 10,000 by 20,000, divide both sides by 20,000. We end up with one half of 24, or 12 meters per second, is V final, once they are both combined into a single unit. Okay, that's how fast they will have to be going after the collision because of conservation of momentum. This is what we saw yesterday in lab. You saw how the momentum after the impact was the same as before. But what about kinetic energy? How does kinetic energy behave in this collision? Well, the total kinetic energy initially is, for this one is 0, but so the total kinetic energy of both of them is 10,000 kilograms, half of 10,000 kilograms times 24 squared, or about 2.88 million joules. That's equal to 1/2 10,000 kilograms times 24 meters per second squared. After the collision, the total kinetic energy is now 1/2 20,000 kilograms times 12 meters per second squared. Which, if you plug the numbers into your calculators, will show you that it's about 1.44 million joules. So the kinetic energy was cut in half in the collision. And that's the whole point of learning and studying the conservation of momentum. is because even when the interactions and the forces involved, don't get the wrong idea. Energy is absolutely conserved. But half of the kinetic energy in this collision got turned into something else. Okay? It did not translate through the collision. So it was lost to friction. A lot of it got turned into sound. It got turned into heat. Whatever happened to it, half of it was lost. Rather than going through and trying to do this quixotic effort of trying to calculate all of the possible losses and quantify them and measure them, and all we got to do is look at the momentum and find out how much of the kinetic energy survived and how much of it, because the potential energy doesn't change. They're both still at ground potential. There's no potential being stored in a spring somewhere. They have the same potential energy after the collision. So we know that all of that half of that kinetic energy that train car had rolling up got turned into something else in the collision. But no matter what happens to that, the momentum that this car has coming into the collision must still equal the total momentum after the collision, no matter what happens to the rest of the kinetic energy. And I showed you yesterday that if you look at kinetic energy, it's equal to 1/2 mass times velocity squared. Well, velocity is delta x divided by delta t squared. Well, if you break that apart, you can rewrite that. Where this is your momentum. This is your velocity. In fact, instead of breaking it down into delta x, delta t, we'll just write it as velocity times velocity. There is your momentum, the momentum part of the kinetic energy. So this other half of the velocity is kinetic energy that is available to be converted into something else. Okay? It might get turned into potential energy, it might get turned into sound, it might get lost to friction and heat, but it can go somewhere else, depending on how inelastic the collision is. This is a perfectly inelastic collision because the two objects stick together after the collision. Okay? If it was a perfectly inelastic collision, then all of this kinetic energy would be conserved. Most collisions are neither perfectly elastic or perfectly inelastic, so some of this energy gets lost, some of it doesn't. But momentum will always be conserved. So, let's look at one more example here. This is kind of the opposite of what we were doing in lab yesterday. Wait, which one of you has the rifles on your leg? That's you. Okay, this one's for you. Here we go. You got a rifle? And it fires a bullet. Let's see, what do they give us? They give us numbers in the example. 5 kilogram rifle fires a 20 gram bullet at a speed of 620 meters per second. Kilogram rifle. What is the velocity of recoil of of the recoil that you will experience when you fire that rifle. Total momentum before you pull the trigger is 0. That means that after you pull the trigger, 0.02 times 620 has to be equal to 5 kilograms times the negative V recoil. And if you do the division, they tell you that it turns out to minus 2.5 meters per second. Is kinetic energy conserved? Think about it. Cyrus, what happens to the kinetic energy in this? Is it conserved? I don't think so. I don't know. Not very likely. Is it a perfectly elastic collision? And anybody that didn't sign the sign-in sheet, make sure you get it and sign it. Oh, well, then I gave you the wrong one. Stop signing into the other class. Who else hasn't signed in? Here. Make sure you pass it over to Cyrus when you're finished. What's the one thing we can absolutely know for certain when you pull the trigger of that gun? Say again?
It's going to drop every time.
What's going to drop? Well, the bullet will eventually hit the ground, sure. But when you pull the trigger, what Ash said, it's going to make a noise. If it produces sound, it's not a perfectly elastic collision. So kinetic energy is not conserved. But if you've ever actually fired a rifle, you know that it is going to kick. And that is the conservation of momentum at work. Now, what word would you use to describe the kick of that rifle when you pull the trigger? Hello? Backfire? No, that's backfire is something else, but a lot of people call it recoil. I would call it an impulse. Who knows what an impulse is? Well, kind of, but it's when you hit a baseball or a golf ball, or when you fire that gun, you do not exert a force, a constant force, or even a varying force over a long period of time. You exert a small amount of force or a very large amount of force, but you do it for a very short period of time. Remember the thought experiment of pushing the box across the floor? And how did you get it started? For a very short moment, you gave it enough of work, you gave it enough energy, you put in enough work to get it moving, and then you only applied as much force as you needed to exactly counter gravity in order to push it at a constant, not gravity, friction, in order to push it at a constant speed. And when you got to the other end and you stopped pushing it, what happened? It didn't stop instantly, it slid just a little bit further because it had that velocity that friction had to stop. And that was friction counteracting the initial work that you did to get it started. So that at the end, when it stops, the total work done on the box is still 0. You did a lot of work, friction did a lot of work, but you both just worked against each other and the net work was 0. Think about that impulse right at the very beginning, that first moment when you give it a boom, a good little push to get it going. What do we know about that? Make sure he gets the sign-in sheet. We know that the force is what? Oh, please, somebody answer this. What's force equal? Mass times acceleration. Thank you. Well, what is acceleration? Change in position per unit time squared. Right? If you take this equation and you multiply it by delta t, you get force times delta t is equal to mass times delta x delta t, which is just mass times change in velocity. So force over a change in time over a short period of time will give you momentum, change in momentum, mass times change in velocity, which is equal to the change in momentum. Okay, that gives us this equation. Force times time is equal to the net change in momentum. This force times time is what we call an impulse. So if you say you've got if you hit a baseball or a golf ball or a tennis ball, and you can measure the force that you hit it with in that short amount of time, then you can calculate how fast that ball is going to be going, because that, if you know its initial velocity, its initial momentum, then its final momentum is going to be its initial momentum plus that amount of impulse. And once you know its momentum, you know its velocity. And I'm pretty sure that you're going to run into at least one or two impulse problems in the homework set. Now, speaking of homework, do many of you have any questions about the homework? Yay, nay? No? Okay. How about the bonus exam? Any of you hadn't run into any questions on that? No?
Aren't you supposed to do that today? Aren't you supposed to do the bonus exam today?
No, I gave it out yesterday in lab.
You told me you were going to give it on Friday.
I'll give it to you today.
Okay.
I'm not going to deprive you of it.
Okay.
But it is due back no later than next Thursday during lab.
Okay.
You can turn in any time before then, but not after.
All right.
After lab next Thursday, it's too late. Deadline is coming up. The end of the semester is here. Now, let's look at the quintessential problem that you're going to run into in momentum, when you study momentum, and that's the elastic collisions of billiard balls. I don't want to go through the whole derivation of this. It's section chapter 7.5. You can read it for yourself. They go through and they do a fairly thorough job of deriving this equation. or this conclusion, head-on, one-dimensional elastic collision, because that happens. What they derive is that the velocity, the relative velocities between the two objects, regardless of their mass, the relative velocities after the impact will be the same as before, but opposite. And they use the example here of the pool balls. Cue ball hitting the, what's that, 3? Yeah, hitting a 3 ball. And they hit it. If you played pool, you've probably done this. If you haven't, then you at least saw it happen on that Newton's cradle I brought last time, where the cue ball hits the ball you're shooting at, and as long as you're shooting in a perfectly straight line, and you're not playing on a coin-operated pool table, if you hit it in a perfectly straight line and you make sure there's absolutely no spin on the cue ball when it hits, what happens? Cue ball comes to a dead stop at the point of impact, and the 3 ball continues on in that same straight line. That is as close as that and Newton's cradle is as close as you're going to get to seeing a perfectly elastic collision. And you can tell me an example when you would actually find real perfectly elastic collisions. When might you actually encounter perfectly elastic collisions in the real world? Obviously, you'll find plenty of them in the pages of any physics textbook. But in the real world, where would you find them? Where would you actually be able to observe a perfectly elastic collision? Anybody? They actually do happen, but only at the atomic and molecular scale. Even there, they're not that common. Even there, when you have 2 molecules collide, they not only do they rebound, but they also get produce little sound waves of the sort of the impulse from propagating through the lattice structure of the crystal. The molecule will start to oscillate in new ways. But you can actually encounter perfectly elastic collisions at the atomic scale. Not in real life, not at the macroscopic scale. But we can find perfectly inelastic collisions. I just gave you a good example of one. 2 train cars. One sitting still, the other one rolls up, they collide and they couple together, they stick together, and they move as one unit after that. Here's another example. The ballistic pendulum, figure 716, example 7.9 on page 181. Who knows what ballistics gel is? Everybody heard of it? If you've ever watched an episode of Mythbusters, then you know what ballistics gel is, because they use lots of it. The only thing they like to do more than shoot things is blow things up. But other ways that people measure the velocity of a bullet is they fire the bullet into a block of ballistics gel. And once the bullet collides with the ballistics gel, it embeds in the gel, and the whole thing swings up to some new height. right out of the gate. Can you do this problem as with conservation of kinetic energy? Absolutely not. Because in this case, you have a perfectly elastic collision. So every last bit of that extra half a velocity worth of kinetic energy is going somewhere. But it ain't going to still be, it will not survive as kinetic energy. But the momentum will. So, you know that mass, right before the bullet, you have this block is sitting at 0, and you have the mass of the bullet. Write it that small or no one will see it. You have the mass of the bullet times the velocity of the bullet is your total momentum before. After, your total momentum is the mass of the bullet plus the mass of the block. There, I'll make it a capital letter, because bullet and block don't really distinguish well in subscript. Times their combined velocity. That is how much kinetic energy they have after the collision, after the impact, after the bullet block lodges into the gel. So you can calculate that initial kinetic energy as the total kinetic energy in the system after the collision. Okay? Has nothing to do with how much kinetic energy you had before the collision. But after the collision, this is how much kinetic energy you have. And that means that is how much potential energy you're going to be able to gain. If you know the height, the change in height, you know the change, you know the gravity, and you know the two masses, then you now know what this number is, and you can solve for that V final. And once you know V final, then you know what the total momentum was after the collision, which means you know what the total momentum was before the collision, and you can then calculate the velocity of the bullet before the impact. Does everyone see how that works? Over here, Giancarlo. Do you understand how that works? How that was done? Good? Sorry? Seriously, if any of you have questions about this, I mean, I'm not plugging in numbers and doing the calculation, but this is how you would solve. Let me rephrase this. This is how you're going to need to solve one of your homework problems. So, do you understand what is done here? Once you get this change in potential energy, that tells you how much kinetic energy you had, which gives you your final momentum, which is got to be equal to your initial momentum, from where you can calculate the initial velocity of the bullet. All right. Now let's talk about collisions in 2 dimensions. And looks like we might actually make it all the way to center of mass after all. many of you have actually played pool? You ever play pool? You ever play pool? Billiards? You've never played? Yeah. Okay. Then the first thing you know immediately, if you've ever actually played pool, is that when you hit the ball with the cue ball, you do not get a perfectly elastic collision in one dimension, because the cue ball doesn't just stop where you hit the ball. And that ball does not move off in a straight line. You're going to hit it off center and cause it to go off in the other direction. And if you're really good, you're going to put some spin on the cue ball, so when it hits the object ball, the object ball doesn't just go off in a different direction, it gets some of that spin too. Okay? We're not going to worry about putting English on the cue ball. We're going to assume that all of our cue balls are English free. Okay? But we're still going to look at what happens when these billiard balls collide in two dimensions. Comes in. This one is at 0. This one has some initial velocity. And because we're not playing, a while ago I mentioned that as long as you're not playing on a coin-operated pool table. Does everyone understand why I said that? Just occurred to me, y'all probably don't. What's different about a coin-operated pool table? Have you ever played on a coin-operated pool table? What happened? What is different about it? When you scratch, what happens to the cue ball? It returns back to you so you can continue the game. What happens when you sink one of the other balls? It goes into the tray and waits for the next quarter or $1 or whatever they cost now. Okay. How does that happen? It happens because the cue ball is just a little bigger than the other balls. Okay. So it won't fall through the hole that they fall through to go into the tray, the chamber where you've got to pay to get them out again. It'll go right on through and come back out with the ball return. Okay. So on a coin-operated table, cue ball is not exactly the same mass as the other balls. So for all of our purposes, we're going to assume, unless the masses are specified, we're going to assume that we're playing on a normal pool table and the cue ball is the same mass as every other ball. Because I promise you, the momentum doesn't care what color it is. It's like the electrical wires. The inspector cares about what color goes where. Electricity could care less. So they both have the same mass. And the total momentum of the system at the beginning is mass times VI plus 0. Well, after the collision, the cue ball goes off in this direction, and the object ball goes off in this direction, both with some new velocity. So here we're going to break this down into horizontal and vertical components. Does everyone remember the vectors and how we do that? You know how to, this is some velocity, V final 1, and this is V final 2. Okay, and they're both vectors at theta 1 and theta 2. Well, the horizontal component of this velocity is V final 2 times the cosine of theta 2. And the vertical component, that's this component of its velocity. The vertical component is V final 2 times the sine of theta 2. Same up here. You've got V final 1 times cosine of theta 1 is the horizontal component of its velocity, and V final 2 times the sine of theta 2 is the vertical component of its velocity. The total sum of the momentum to begin with was mass 1 times V1, all horizontal. That was the horizontal. There's no vertical component to it whatsoever. Now we have two horizontal components, V1 final times cosine theta 1. We've also got this horizontal component, V final 2 times cosine theta 2 times, well, actually now it's times 2 times the mass because you've got twice the mass involved. Here you only have one mass in this total momentum. Afterward you have two masses. So it's the total horizontal momentum after the collision is this. The total vertical momentum after the collision is two masses times V final 1 sine theta 1 plus V final 2 sine theta 2. Now, if we do these as vectors, where we combine these into these horizontal and vertical components into a single vector, then we could get them and we could do that and turn it into a magnitude in some net direction. And we would know they would have to be equal to this. Okay? Instead, what we're going to do is we're just going to treat the horizontal and vertical components independently. This is completely horizontal motion here. We choose the axis, the x-axis, in line with this initial velocity vector so that it becomes the only component of the initial momentum. And that means that mass M1 times V1 times V initial, V1 initial, has to equal all of this. 2 times mass times V1 final cosine theta 1 plus V2 final cosine theta 2. We also know that the initial vertical component of momentum was 0. And so that has to equal all of this. 2 times the mass times V1 final sine theta 1 plus V2 final sine theta 2. All this tells you is that V1 final sine theta 1 has to equal minus V2 final sine theta 2. My 2's keep looking like A's. Alright? Everyone see how I got this? This is equal to 0. So the first thing I do is divide both sides by 2m. 0 divided by anything is still 0. So in other words, I'm saying this cannot possibly equal 0 as long as we have, as long as the masses are not 0. And that's never going to be 0. That's not going to change. The only way for this to equal 0 is for this part to equal 0. And for that to equal 0, that has to be true. Same over here. You divide by m, and you get your V1 initial will have to be equal to one mass times all of this. And if in the problem they gave you enough information about initial velocities and the angles that they both reflect at, then you should be able to solve for whatever part you don't know. Let me ask you this, just a general math question now. How many of these unknown variables can you possibly solve for? This is something every one of you should be able to answer just off the top of your head without even thinking twice about it. What is the maximum number of variables you could solve for with this problem? Say it out loud. Two. Why? Say again. Who can tell me why 2? I know you know because we've discussed this. Why can you only solve for two unknowns in this equation, in this system? That may not be the answer I want to hear, but at least that's the right answer. No, seriously. Write this down somewhere, stick it in the back of your memory, and remember it. The hardest part of being right all the time, and if you want to be right all the time, the hardest part is learning that I don't know is usually the right answer. So, Garrett Kusat was correct. He was guessing, but he was correct. You cannot solve for more than 2 variables in this system, but the question is why? The reason is because you have 2 independent equations. If you have 2 linearly independent equations, you can solve for at most 2 variables. So if you've got a problem and they're asking you to find 2 variables, then you know you need to have 2 equations that you can solve for. And if they're asking you for more than that, then there's got to be another equation somewhere that you haven't figured out how to write out yet. So that's what you need to look for. Now, last topic before I turn y'all loose to go out and slaughter your homework. I know every one of you is going to kill it, right? I'm using that correctly. That is a good thing, right? Okay. I haven't been young and cool for a long time, so. It would be a very bad thing to think I was saying something that was a good thing and then find out later that I was making some kind of terroristic threat. So, who can tell me what center of mass is? Okay, better question. Everybody look up. What's the Fosbury flop? The Fosbury flop. It is not a dance. Well, you can make one up and call it that.
It sounds like a dance.
It sounds like a description of me dancing, but no, that's not what it is. Who knows? No one's ever heard of Fosbury. Fosbury, okay, somebody bring out a phone and do a Google search. Fosbury was a track and field athlete, and he revolutionized the high jump. And the way he did it was by going over the bar backwards. There you go. See, you thought I was making stuff up just to get you, just to confuse you, right? What he did was he figured out that he didn't need to jump as high, he didn't need to jump as hard to go over the bar if he would go backwards. Why? Because all you have to do is get your body over the bar. But if you arch your back like this, your center of mass, now in my case it doesn't work because my center of mass is way further forward than it used to be. But for someone skinny like y'all, if you bend your back like this, then your center of mass is actually somewhere back here. Okay? If you take a oddly shaped object, like a big old crescent moon cut out of plywood, where's the center of mass? Somewhere in the middle. Center of mass is where there is no mass, but it is the point at which you could treat, you could mathematically solve for how this thing will move or be affected by forces if you apply that force to a point object of equal mass at the center of mass. Does that make sense? If you have some oddly cut out shape, like so, and you want to know where the center of mass is, hang it from 2 points. If you hang it from this point, and you draw a line straight down, and then you pick it from here and you hang it, and you draw a line straight down. Where those two lines intersect, that is your center of mass, or your center of gravity. Depending on who you ask, they may say those aren't quite the same thing, but they are. Fosbury figured out that he could actually get an extra several inches by arching his back like so, going over the bar. So when he would jump, he would turn and he would go over the high bar backwards, and he would arch going across. And while his body went over the top of the bar, his actual center of mass passed several inches under the bar. So he got over a higher bar with the same amount of energy expended in the leap. And it was so bizarre. It was just absolutely, nobody else had ever seen anything like it. But he was jumping higher than anyone else. And so somebody finally figured out how he was doing it and what was going on, and they called it. But by then they named it the Fosbury flop. Because that's what it looked like he was doing. It looked like he wasn't jumping over the high bar. He was just flopping over the high bar. And it was like they would be laughing at him and making fun of him because it didn't look at all cool and elegant like all the other high jumpers. But it was higher. But he was still jumping over higher bars than they were. And that's where center of mass came into play for the track and field. How do you calculate the center of mass? You can actually do integration to get it. We're going to look at discrete masses. The center of mass is a position X in space. We're going to say we're going to treat it as a one-dimensional problem right now. X is the x-axis. And if you've got several masses, so you've got 2 or 3 or masses lined up along this x-axis. Their center of mass is going to be let me make sure I wrote that correctly. Yep. That's for any number of masses lined up in a row. You can actually take this and extrapolate it into 2 dimensions. I don't think we're going to be doing any 2-dimensional problems. So, oh, look, they showed me. Look on page 186. Figure 724, 725. That's what I was showing you just a minute ago. Anybody have any questions about how you calculate the center of mass for several objects? What if they were scattered out in 2 dimensions? Well, the center of mass along the x-axis would be this. And then you write out a center of mass equation for the y-axis and find out the center of mass along y. And the center of mass for the whole system would be at that point. X center of mass and y center of mass. But like I said, I don't think you're going to run into any 2-dimensional problems in the homework. Any questions? Yay, we made it all the way to it. Bonsoir, have a good weekend. You know where my office is if you run into any questions. Need help with anything. And everybody make sure you sign the attendance sheet before you leave.